Yeah. Well, thanks everyone for coming. I'm happy to present Dr. Miguel de Icaza. I did my PhD with him in Durham, and now he's at the Korean Astronomy and Space Science Institute for his first postdoc. And he's going to tell us today about his work for DESI. Thanks.
Well, hello, everyone. Thank you very much for being here. So yeah, I'm Miguel de Icaza. I am a first-year postdoc at CASI, where I've been working with Professor Jong-Seon Song and his group. I'm also in some other collaborations. Most recently, I started working with Celine and her work here and her group here, and that's part of the reason why I'm visiting you today, guys. So over the last couple of years, I've been involved in some large-scale structure surveys, which are a type of astronomical survey that I will introduce in a second. And as part of my job, I've been doing several machine learning applications to cosmology. One of these applications are known as emulators, and I'll introduce them in a second, and I'll tell you a little bit of how we use them for DESI. But before I start, I want to spend the first part of this talk introducing to you guys a little bit about large-scale structure surveys, a little bit of why do we cosmologists care so much about them, and why do we hope to learn from there. And in particular, I want to introduce one of these surveys, which is DESI, the Dark Energy Spectroscopic Instrument, which is a survey that I've been working with for the last year or so. And it's a survey that has been run in Kitt Peak National Observatory in the United States. And so the idea of a large-scale structure survey is to look at a patch of the sky and to measure the distance to galaxies within that patch, as it's represented in this image here, where there's like this cone, and in the center of the cone we have Earth, and then each point in the image represents a different galaxy. And so the idea is that if we measure the distance to enough of these galaxies, the underlying structure of the universe will appear within the survey. And so we will, for example, see regions of the universe where there's a lot of galaxies clustered together, other regions where it's probably a bit devoid of galaxies, regions of filaments connecting clusters to each other, and so on. And we want large-scale structure surveys because we want to study this underlying structure. Well, DESI, it's one of the newest large-scale structure surveys that is being built at the moment. In some years, when the data collection stops, it's going to be the largest survey done to that date. And we hope to measure the distance to somewhere around 40 million galaxies or so. This is a bit of a schematic of the DESI instrument. We have around 5,000 robots. Each of these robots is connected to a spectrograph. And the idea is that when we're pointing at the night sky, the robots move and point towards a specific galaxy. And then the light of the galaxy passes through the robot into the spectrograph, and we collect the spectra. As an example, I am showing here one of the DESI press releases. It's from a quasar that they detected at a very long distance from us. So I've been talking about measuring distance to galaxies, but I just mentioned that what we actually get is the spectrum. And so for those of you that are not that familiar with astronomy, I want to just spend a minute trying to explain how we can compute distance from spectrums. This is related with one of the most famous results in cosmology, which is the Hubble law, which basically says that because we live in an expanding universe, the relation between the velocity at which a galaxy is receding from us and the distance from us to the galaxy is a linear relation ruled by that constant, which is a Hubble constant, and there's a lot of cosmological effort that goes into trying to measure this constant as accurately as possible. And so if one will have a measurement of the velocity, recession velocity of an object, we can transform that into a measurement of the distance. Luckily for us, when galaxies are receding from us at a given velocity, this generates a Doppler shift in their spectrum. And so the features that we normally see in the spectrum, the emissions and absorption lines, are deviated a little bit to the red end of the spectrum. And by measuring that deviation, so we know where these lines should be if the object is static. And by measuring that deviation, we can get an estimate of the velocity, which then we can convert into a measurement of the distance. Okay, and what's the idea behind all of this? Why do we actually want to make these complicated three-dimensional maps of the universe? The main motivation is to be able to test different models of cosmology and to constrain the parameters of these models. I want to make a bit of a pause and try to explain a little bit to those of you that are not that well-versed in cosmology, what do I mean when I'm talking about a model of cosmology. And in order to do that, I'm going to introduce probably the most famous model of cosmology, which is the Lambda-Sirian model. It's for sure one of the most tested ones and agrees with most observations, almost all of the observations. And this model suggests that we live in an expanding universe and that general relativity is the correct law of gravity. And so interactions between galaxies should be determined by that law. So if we make both of these assumptions, we have to propose the existence of two new energy components in the universe. The first one that we call dark energy needs to be included to explain the accelerated expansion of the universe, which is something that we discovered some years ago. And so when we were trying to measure the expansion of the universe, we were expecting that it will be decelerating because galaxies are bounded together with gravity. But instead, we measured that the expansion is accelerating, which is a bit anti-intuitive. And in order to explain this, the Lambda-Sirian model proposed that there is a new energy component. We don't really know what it is, but it should act as a sort of a pressure force that makes the expansion faster. Another component that we propose, and most of you guys are very familiar with this one, it's dark matter. And basically, the idea is that when we look at the dynamics of galaxies and galaxy clusters, we see that the way in which galaxy moves corresponds to a much more larger mass than the one that we observe from observations. So if we measure the mass of galaxies like stars, gas, and such, we don't have enough mass to explore the dynamics that we see. So this model suggests that there is another type of matter that hasn't been detected yet. It probably doesn't interact with light, or at least interacts very weakly, and therefore it's very hard to detect. And so you guys might imagine that, okay, we have this model with these assumptions, but there are many other assumptions that one could make. Some people suggest that probably instead of including these new components, we might suggest that GR needs a slight modification or something like that. And in general, there's many models, and all of these models have many free parameters. And what we want to do with large-scale structure surveys is having a way of comparing all of these with observations. So as a way of showing this, here is an image of the TDF Galaxy Survey. It's a survey that happened some years ago. It's a bit old by now. But what I wanted to show is how in this survey, each blue dot represents a galaxy. And you can see, as in the first slide that I show, how there's regions where galaxies are clustered together and voids and such. And one can imagine that different models with different values of their parameters will predict a different clustering pattern of those galaxies. So for example, if we were to suggest that there is a more dark energy or dark energy, then the distance between different structures will increase faster, and therefore the pattern will be different. If we include dark matter, then maybe the galaxies are more tightly bounded together than if there isn't, and so on. And so the idea is that we measure the clustering pattern from observations, and then we compare it to what we get from different models, and hopefully we will see that some models agree well with what we observe. So I've been speaking a bit about the clustering patterns of the surveys, but now I want to be a bit more specific, and I want to introduce the statistic that we normally use for this. There are several statistics that are used in the literature. One, possibly the most famous one, is the correlation function. One can understand the correlation function as the excess probability of finding a pair of galaxies separated by a given distance. And so if one were to have just a completely random distribution of galaxies within the universe, then the probability of finding two galaxies at a given distance will just be the product of those volumes times the average distance, the average density of galaxies squared. But if we actually have a pattern within the universe, if it's not a completely random distribution, then that probability will be modified, and it will be modified by the correlation function, which is that term that I'm showing in the equation. An equivalent way of defining this, and this is a way in which you can actually measure it from like a large-scale structure survey or so, is by by considering the ratio of actual pairs that you measure in a survey with what you will expect out of a completely random distribution. And so the idea is that if you have your galaxy survey and you want to know how many, you count how many galaxies are separated by a given distance in a distance bin, and then you compute how many you will expect from a completely random distribution, the ratio between those two will give you the correlation function. And then finally, other equivalent definition that I'm not going to prove. If you guys are interested, it's you can go and any book on cosmology should derive this equation. Is an equivalent definition is the expected value of the overdensity field at the two different points. Okay, and then one last remark that I want to make is that some people work in with the correlation function, and some people work with the correlation function on the Fourier space. There's different operational advantages to one or the other, but in here I am just gonna show some results in one or some of the other, and it's an equivalent methodology. Okay, so I've mentioned that we want to measure large-scale structure surveys to compute the correlation function of data, and we want to compare that correlation function with the correlation function of models to see how well these models agree with the data. So the next thing that we need, it's a way of computing the function from models. There's several ways of doing this. In this talk, I'm going to focus on two, which are probably the most important ones. The first one, it's embodied simulations, and I'm sure a lot of you guys working with physics might have encountered embodied simulations at some point. And an embodied simulation, it's a virtual universe. So you have a virtual box where you place matter representing the distribution of density that you believe the early universe will have. And then you ask, you explain to your computer the different laws of physics within your model. So if, for example, if you're in lambda CDM, you will explain to the computer how gravity works in lambda CDM or whatever. And then you will ask your computer to compute the dynamics of all of the particles within that simulation by interactions with particles surrounding it. And so if you do that enough steps of times, what you will see is a pattern like the one that I'm showing here in this picture from the Eagle simulation, which is one of the most successful hydrodynamical simulations. And so at the beginning, you have a relatively homogeneous universe, and then as time starts to pass, small overdensities at the beginning of the universe start to grow, and the overlying large-scale structure of the universe starts to form. So this is probably the most accurate approach that we have, but it is also a very expensive approach, depending on the stuff like the resolution of the particles that you want, the volume that you want, the type of interactions that you want to include. Hydrodynamical simulations can be very, very expensive. And so embodied simulations can be very, very expensive. This is going to be important later on. And so another way of computing the correlation function is with perturbation theory, which is probably a cheaper approach, depending on how you do it. But the very basic idea is, again, within your model, you should have some equations that describe the motion of and the dynamics within your system. And these equations should depend, for example, on the density or on the velocity and so on. Let's say that we are thinking just of Newtonian models, simple lambda CDM models. Then maybe you will want mass conservation equations, momentum conservation, whatever equations you think that can determine the dynamics of your models. And then the idea is to try to solve those equations and try to find the values of the density that they can then use to compute the correlation function. But this is obviously very complicated. And so what perturbation theory, people working on perturbation theory suggest is that the quantities that you're interested in finding, for example, the density field or the velocity field, can be written as the quantity at the mean quantity at the time plus a small perturbation. And so when you do that, and then depending on what you want to use this for example, if you're in like very large scales, or if you're in like in a very early universe, then maybe this perturbation can be considered small, and therefore stuff like the quadratic terms of when you're trying to solve the equations and so will disappear, and and you will end up simplifying your equations a lot. In reality, this is a good approach when we have what we call first and second order perturbations, which are including the linear and the quadratic terms of these distributions. When you try to go to like higher order, third order, fourth order, stuff starts to become more complicated. And in general, if you are interested in this, you can, for example, for the lambda CDN model, you can go online and there's a bunch of free codes that do second order perturbation theory for you that you can just download and run on your computer. But yeah, then higher orders get slightly more complicated. And this is important because with the new resolutions of surveys like DESI, higher order correlations start to be necessary. And that's a problem that we're dealing with. Okay, so I mentioned that we want these large-scale structure surveys to study the clustering patterns of the universe. I mentioned how can we compute these clustering patterns in the form of the correlation function for the surveys, and how can we also compute it from models. And as I mentioned, we want to do this for two reasons. The first one is to constrain the parameters of a given model. As a way of showing this, I am showing for one of the models that we are currently using for our DESI analysis. It's not important what the model is. It's one of our perturbation theory models. I'm computing the correlation function at a given cosmology, and then just varying some quantities in the left, the density of dark matter, and the right, the density of baryons. And then what you can see is that the correlation function varies drastically. So one can imagine that if you had measured this from data, you will have your data points with some errors around here, and then this will help you constrain the values of your free parameters. And that is sort of like one of the main reasons why we want these surveys. Another very important reason is that we might want to see if a given particular model agrees with our observations. The theory behind how we do this is a bit complicated. I probably don't have time to summarize it in a couple of minutes, so I'll just do like a very broad sketch of what's happening. But this basically relies on two features. The first is what is known as the baryon acoustic oscillation peak. For those of you guys that have been observing some of the plots that I'm showing, you might have noticed that all of the correlation functions that I've shown have a bit of a peak, somewhere around 100 megaparsecs. As I just mentioned, this correlation function can be interpreted as the probability of having two galaxies separated by a given distance. So this peak means that for some reason, it is more likely to find two galaxies separated by this scale than on other scales. The reason behind it is very pretty. I don't know if I have time to summarize it very well, so I'll just do like a very quick explanation. But the idea is that in the very early universe, when baryons and photons were still coupled together, we had small overdensities of dark matter. And then because the baryons feel the gravitational attraction, they started to collapse into this dark matter, but they were still coupled with the photons. So the photons also came along for the ride. And at some point, the photons were so compressed that the thermal energy was very high. And then there was a sound wave expansion. And so the sound wave is expanding. And at some point, the baryons and the photons decoupled. And so this like cloud of baryons stays around the center of these overdensities. And this explains the peak that we find. So I know that this was like a very fast explanation, but the important thing that I want to highlight about this is that within a given model, this scale, the position of this peak can actually be determined. This is because it only depends on stuff like the time scales in your model, like when are stuff decoupling from each other and that kind of stuff. And also because, and it also depends on like stuff like the speed of sound and such. And these are all things that within a given model you can actually determine. And so this means that you actually know the size of the BAO scale. And so if you are doing a survey of galaxies and you have different tracers at different redshifts, you can actually measure this size in all of your given scales. And so if you have the apparent size of something and you know the real size of something, that is enough trigonometrical information to like measure the distance. So you can measure the distance to a bunch of different stuff, and you can use this information to track the expansion history of the universe, which is, and that's great and all. But we've known for a while that different models of cosmology can predict the same expansion history if we have the right relation of pressure and density. And so if we wanted to know if a given particular model agrees with observations or not, we need another parameter that breaks this degeneracy. Commonly, the parameter that is used are parameters that quantify the amount of structure that has been formed at a given time. And we can think about it in this way. Let's say that we have two different universes, one, for example, with dark energy and one without dark energy. And we see a certain structure at a given time. Because the universe with dark energy had like a force that was like making everything further and further apart faster, then the collapse will have to, the formation of structure will have to have started a bit earlier in order to explain the structure that we see today. And so the idea is that if we have something that can tell us some information about when was the structure formed during the evolution of the universe, we can break this degeneracy and we can now tell if our models agree or not. Luckily for us, this information is encoded in the peculiar velocities of objects. And so we can, so you can imagine that when a structure has been forming for a while, things are more collapsed and everything moves a bit faster. And so the peculiar velocities of that stuff are a bit faster than if the structure is just starting to form. And so if we could find some information about the peculiar velocity of the objects, we can probably introduce this in our models and break that degeneracy. And then there is, and then this information is actually stored in the spectrums that we measure, because the idea is that because when we are measuring the distance to a galaxy, we use the spectrum and we look at the redshift of that galaxy. We are considering that all of the redshift is due to the recession velocity of the galaxy, but we are not considering that maybe that galaxy also has a peculiar velocity of its own. And those peculiar velocities also have a component. And when that velocity happens in the direction of the line of sight that we're observing, then that will also have a contribution. And then because of all of this, what happens is that when we look at structures in the universe, they are a bit distorted. Because every time that something is moving along the line of sight, we are measuring its distance with a bit of an error. But when that peculiar velocity is perpendicular to the line of sight, we don't. This is known as redshift space distortions. And so this is a bit of a cartoon of redshift space distortions. Let's imagine that you have like a sphere of galaxies and they are collapsing. What you will notice is that galaxies that are moving in this direction are not really distorted. So across the line of sight, the sphere looks the same. But then the distortion happens in this distance, and then the shape of the sphere becomes like a bit of an oval. Eventually, when the structure has really has formed like a lot, then the peculiar velocities are very fast, and the radius of the overdensities are probably not that large anymore. And so the correction is even larger than the radius of the overdensity. And what we see is like these oval structures that are called fingers of God and are very famous in surveys. And so hopefully that was not very confusing. The conclusion out of all of this is that because of this component of velocities across the line of sight, when we measure the correlation function, we have some distortions. And this means that now our correlation function depends on two free parameters. One is the distance between the objects, and the other is the line of observation that we have between those objects. And this is a bit of a mess because obviously now correlation functions are more difficult to interpret, but it has the other advantage of like allowing us to have some information about these velocities and then for break the degeneracy. Okay, so hopefully that gave you a bit of an idea of why are large-scale structure surveys so useful for cosmology and why there's so much interest in making them as accurately as we can. I'm going to spend now a couple of minutes just trying to explain a schematic of more or less how the work that one will do in a large-scale structure survey will look like. Basically, in order to do the analysis, you need three components. We have spoken about the data already to go measure the distance to a bunch of galaxies and compute the correlation function. We've talked about the model. You have a model that has a set of free parameters. When you switch those parameters, your model change, and you want to find the parameters that better fit the data. And finally, you have a set of errors. I haven't really talked about how you do this. The main summary, the main idea is that you use these techniques known as quick mock techniques. Basically, you come out with these methodologies that can generate predictions of the power spectrum fast and efficiently. You try with different initial conditions, run it thousands of times, and then you get thousands of power spectrums that you can compute the correlation function from, and you have an estimate of your errors. And so you have data, models, and errors. You can start doing stuff like goodness of fit estimators. For example, the chi-square is pretty useful. And if you can do so for a given value of the cosmological parameters, you can do a goodness of fit estimator. Then you can start doing stuff like exploring the parameter space, most commonly with a Monte Carlo Markov chain that I'm sure most of you guys are familiar with. So this is the very basic idea. You explore the parameter space and you find the values of your model that better fit the correlation function that you observed from data. This is a result that we have from the 14th data release of EVOS a couple of years ago. And so what I've just mentioned is that in order to do this analysis, you need to explore the parameter space of your models very thoroughly to find the regions where these are the better fit to the data. You normally do this with a Monte Carlo Markov chain or so. And here, one of the issues of doing this analysis is that for the new models, that the new generation of models that is going to be used in DESI, they depend on a lot of free parameters. There's, I don't know, 10, 11 free parameters in some of these models. And also the correlation, these free parameters are not as uncorrelated as we would like them to be. So the amount of points that you need to explore the parameter space is very, very large. Sometimes you need hundreds of millions of evaluations and such. And so you really want very efficient models because you're gonna compute them a lot. But then, unfortunately, the best models that we have are probably not the cheapest ones, are actually probably the most expensive ones. That's why they are so good. And so you need to come out with ways of learning how to evaluate these models efficiently. And very recently, machine learning techniques have been used for this purpose. This is an example of another work that I'm doing with some people in Mexico, in which we're using neural networks to do this. The very basic idea is that you have the parameter space, very complicated parameter space of 11 free parameters or such. And then you explore the parameter space and you have different correlation functions. You feed all of the parameters and the correlation functions to your neural network, and the neural network learns how to predict the power spectrum. And so neural networks, when used properly, they can be frighteningly accurate at predicting the power spectrum. This example that I'm showing here, so the line corresponds to the percentile error line. So basically, we got a test set of points that were not used for training the emulator. And we got like thousands of them, asked the power spectrum to the neural network to compute their power spectrum. And then we compare them to the real one. And we can see that the error on like most of these power spectrums is less than 0.1% or something like that. So they can be very, very accurate at doing this. However, in order to train neural networks accurately, you need tens of thousands of points or something like that. So for certain models, there's not an issue, but when you have something like an embodied simulation that you can probably run one per day or something like that, you're probably not going to find tens of thousands of those. You're probably only going to use, I don't know, 100 or such. So we need to come out with other techniques for doing this. And so in the remaining of this talk, I'm going to explain a little bit of how of what was the methodology that we followed to build these emulators for a given model. This model, we call it the hybrid model. And it was a model that was generated in my institute a couple of years before I arrived. And the problem with emulating this for building models for this emulators for this model is that you actually require embodied simulations, and therefore it's expensive to generate training data. Okay, but before I start, I just want to give a very brief introduction to the model. I'll be very brief. I'm not going to go into details because it can get very complicated. But the idea is this: as I mentioned at the beginning, we've been able for a while to do second-order perturbation theories very accurately. However, as I just mentioned, second order is not enough for the accuracies that we want in new surveys. And so we would like a way to compute the higher order corrections. And so what my supervisor and his team suggested is that if you could compute these corrections at a given cosmology, then there's a set of scaling relationships that he suggests that can help you compute the power spectrum in a different cosmology with different values of two cosmological parameters. And the trick is that this works when these parameters only affect the amplitude and the scale of the power spectrum. And so the idea is that if you, the idea is that this will reduce the number of parameters that you need to treat, because now these two parameters are out of the equation. And so what he suggests is that if you were to compute in a fiducial cosmology and n-body simulation, you could approximate the higher order corrections as the difference between second order perturbation theory and this accurate n-body simulation. And then these higher order corrections can be transferred to other cosmologies with the scaling relationships. This is a bit of a schematic of how the model that we're trying to emulate works. Basically, now you have your hybrid model, which is the one that I described, and it requires two inputs, one from an n-body simulation and one from a second order perturbation theory template. But these only depend on 3 parameters, and then the rest of the parameters go in the hybrid model. And so if we look at the time that each step requires, the hybrid model is pretty much automatic, so we don't really need to emulate that one. And then the n-body simulation is the slowest part. That requires probably half a day to generate in our computer cluster, and it's a shared cluster. So maybe if we generate more than 30 or 40, everyone in our institute will be mad. So we cannot generate a lot of those. And then we also require second order theory. This one is much faster. I can generate maybe in 5 minutes, I can generate a template. But again, I need millions of those. So maybe I would also like to emulate that one. And so as I said, the bottlenecks are n-body and the second order perturbation, and those are the ones that we're going to emulate. And we're going to emulate them using this technique known as Gaussian process. For those of you that have a bit of knowledge of machine learning, you maybe have heard about this technique in the past. It's used for a bunch of applications. And so Gaussian processes works as an interpolator. And this is important because the idea is that in order to make a good prediction, you need to have previously measured a point that is relatively close. But this is, and so this means that you need to sample your whole parameter space very thoroughly, but you also need to do it with as little points as possible because each point is a new n-body simulation. And so you need to come out with a way of exploring your whole parameter space with very little points. So the methodology that we use for this is a methodology known as I don't know how to pronounce this. I might be butchering the name, but Ailing algorithm, something like that. I'm going to go through a rough schematic of how it works, but if someone wants more details, they can find them in this paper that I'm citing here. And the idea is that one starts with a symmetric Latin hypercube, and I'm sure it sounds like a complicated name. The idea is very simple. A Latin hypercube is like Sudoku. You have a box in your parameter space, and then you place points in such a way that for every row and every column, you only have 1 point. So if you guys look at this plot that I'm showing here, you will notice that that there's no 2 points at the same altitude, not at the same, at the same X or Y direction. And so that's a Latin hypercube. An asymmetric one is simply one that if you see at the projection through the center, if you have a point, the projection through its center is also a point in your grid. And so there are several Latin hypercubes, and you want to find the one that it's a good, that fills the space very good. And so what the algorithm does is it selects a dimension and then exchange 2 points within that dimension. That's shown here. The pink points were the previous points, and then you switch their position in one dimension to get the green points. And then because you want to conserve the symmetry, then you also look at the reflections through the center and you also change those. So that idea is very simple. And then, but once you do a switch, you might have a better parameter space, a space that it's more thoroughly explores your parameter space, or a worse one. And you quantify this by just like computing the average distance of all of your points. And then what you try to do is you try to maximize this metric. And then what the algorithm does is explore the parameter space of different possible permutations, pretty much like in an MCMC. You do a change, and then you look at if it's better or worse. If it's better, you keep it. If it's worse, you might discard it with a probability. You explore the parameter space of permutations, and you end up with a much better shape, with a much better grid that explores the parameter space better. This is slightly dependent on initial conditions, so we run 40 random symmetric lighting hypercubes, and we do these 40 times. Okay. So once we have selected our grid, we have a set of endpoints in our parameter space, and we build an n-body simulation in each of those points. And so we have a set of n power spectrums. And now we want to learn how to emulate the power spectrum. And we want to do this with Gaussian process. But before we start, if we will try to emulate the power spectrum directly, for those of you that have worked with this sort of data in the past, you require like 100 values of the wavelength. So you will have to make hundreds of predictions. And that's probably very complicated for the code and unnecessary. So a better way to do this is to express your matrix of power spectrum as eigenvalues and eigenvectors, doing a singular value decomposition. And then if you do this correctly, then the first vectors do most of the modeling, and just a small subset of, and the other vectors are just a very small correction. So in our case, we have found that like the first 5 vectors do most of the modeling, and then we have a very small error for the rest. Some important thing to notice here is that the dependency on the cosmology only comes in like the eigenvalues of the eigenvectors. So that's just a number. And so we only, for each point in parameter space, now we only need to predict 5 eigenvalues, and we will build 5 Gaussian processes to predict this. I'm gonna very briefly describe the process behind Gaussian processes. The math can get really complicated, so I won't go into details, especially because the error of the whole methodologies like goes into all of the 5 different predictions in a strange way. But the very basic idea is that, let's say that you have a set of the weights that you're trying to compute for values of the cosmology, and we want to compute the new weight for a new value of the cosmology. You build sort of a kernel function that basically tells you, because you're doing an interpolation, so basically it tells you how close 2 points need to be for them to be useful in the interpolation. So you can imagine that if you have a point and you're trying to guess, and you have a point that is at some distance, you want to know if this is close enough to assume that they are similar or not. And so you want a function that tells you that. These functions are called kernel functions. There are different shapes of those. This one is the one that we're using. It depends on some free parameters, and then you can feed those free parameters to the data that you have. But anyways, the assumption behind Gaussian process is that the weights that you are trying to find are a multivariate Gaussian normal distribution that is a function of your kernels. And then you can go and look at the maths, and you follow the procedure, and you have the posterior distribution of your weights. It's also a Gaussian distribution. And then you can find the mean and the standard deviation. Okay. And so this is important because in this plot, I am showing a very easy example for one of the Gaussian process tutorials, where basically you have a bunch of training points, and then the blue line will represent the prediction of your Gaussian process, and the blue volumes represent the prediction of the uncertainty of the model. And so the beauty of these Gaussian processes is that they give you an estimate of in which points your predictions are not very certain. Where does the emulator believes that the prediction could require some improvement? And this is good because we want to use as little points as possible, and this let us know which points we'll have to explore even better. Just to finalize, I'm going to show some results. So this is our prediction for our n-body simulations. We find out that we only need something around 12 n-body simulations to be able to emulate power spectrums in all of the space that we want. which is yeah. And so and we can also do that for regardless of redshift. And then in these plots, I'm showing the bottom of this plot shows more or less the error, and we can see that the accuracy is crazy good. We have 0.1% accuracy, which is a bit surprising, and I'll explain why is the accuracy so good in a second. But first, I'll show some results for second-order perturbation theory as well. We see that the accuracy is also very, very good. In this case, as I mentioned, we are not that constrained to the amounts of points that we can do, so we just generate 120 training sets and 100 test points. And so I guess the conclusion that I want to get to is that when we are, and that we can emulate the inputs of this very complicated model with a very small amount of n-body simulations accurately. And the reason behind this is mainly two. The first one might not be a surprise to a lot of you, is that the Planck constraints are already very, very tight. So even if you move like 5 sigma away from the Planck constraints, the power spectrum don't vary that much. And the second one is that using our hybrid models, we only need to emulate in a 3-parameter space. And therefore, both of these things combined makes that our emulators can be built cheaply and very accurately. So I leave my conclusions here, and I want to thank you very much for your attention, and I'll be very happy to answer any questions that you might have.
Yes, are there any questions on Zoom? I think this was just for the audio.
Yeah.
There's one there. I don't know what's no. Anyone in the room, any questions? Oh, no.
So the reason you can describe the power spectrum with just this principal component analysis instead of making K values, is that because the shape is pretty simple, or can you do it again?
Right. So the question was that why can you grab your vector of power spectrums and explain it with a very small subset of principal components? And then the question was if this happens because of how little variation is on the with the parameters that we have from Planck.
That may be also because the power spectrum itself is just so nice and smooth, but it's not like a very narrow.
This technique has been used for a while, and 5 principal components have been used since 2010, I think. And at that time, definitely the power spectrums were not that smooth. The constraints were not that good.
Could you do that with, for instance, the CMB power spectrum as well? Is the CMB power spectrum?
I don't know. I will. So this is the matter power spectrum. I don't know. Maybe potentially. I don't know. I don't have a good answer for that.
Trying to get my head around the final results that you presented to see. So you have great accuracy at reproducing the power spectrum. It seems like you were saying that the accuracy is kind of being leveraged by the fact that the Planck effects on these parameters are already very high.
Yes.
Is that so? The Planck parameters you're referring to, are these like just parameters of lambda CDN, which are going into the state expansion history?
I am referring to so our n-body simulations depend on 5 parameters, but the only ones that we need to vary is the density of cold dark matter, the density of baryons, and the ns of the initial shape of the power spectrum. Yeah.
So I guess that the question is, do you know what happens if you then have a deviation from lambda CDM, where you wouldn't necessarily be able to rely on that, like two Planck potentially be measuring for slightly different things?
No, but we might be interested in trying to do this for non-lambda CDM n-body simulations at some point, but not at the moment. Yeah.
So the purpose of this is to basically make more measurements of better measurements of parameters on the CDM.
Sorry?
Using DESI to make measurements essentially the same fundamental parameters like I've seen about the
Yeah. So okay, so the thing is that this is the first year of DESI, and the analysis that is being run at the moment is just RSD with lambda CDM, but there's other so some teams are trying to go beyond that, including, I think that some teams are trying to include neutrinos and stuff like that, and yeah.
Another thing is in DESI, people having serious conversations about doing like 3-point, 4-point correlation functions.
So I'm not the right person to ask, but yes, there is 3-point correlation function papers coming out. And also new clusterings that are probably not correlation functions, new statistics that are probably not correlation functions are also being explored.
So just from my understanding, can you go to that illustrate plot that showed the short, sorry, the one there with the balloon out of this one. So I understand this is an illustrative plot. But is it correct that you're using something like this plot to decide, using some metric, whether there needs to be an additional point, and if so, then where should that point go?
Yes, well, there's some difference between this plot and like the ones that we're using. For starters, there is no error here, and so we actually have some error on the. So in here, the points that you have observed are like, in reality, you have like some errors that also propagate in all of the space. We are using something like this plot in 3 dimensions to estimate new points, and also to test our methodology to know which points the emulator doesn't believe that it can estimate very well. And so we run an embody simulation there. We see how well does the emulator predict that point, and that way we are testing where the emulator is less confident that it can do well predictions, good predictions.
So is this done using some sort of non-trivial process, integral over this, or do you just go to the largest?
There's
the largest error range.
So that's a good question. There's different ways that you can do this. You can weight certain regions where you care. So for example, you might want to make sure that you are doing 3 sigma away from Planck good. You probably don't care that much about 5 sigma away from Planck or whatever. At the moment, so our first test was without any weights, just like the largest point, which was 5 sigma away from Planck, and we were able to reproduce it. So we're probably going to stop there. But yeah, we were, that's it.
So then let's back on Kieran's question about, like at the moment you have run this CDM or scalability to plan funding time. So by doing this to the side, you're going to increase the precision measurement of the bound and measurement component. And I was wondering what is the gain compared to planning.
Right. So what we want is better models in general. Probably like, I don't know if they care that much about the Planck parameters as they care about other parameters like the RSD parameters and such. But like in order to have like very accurate measurements of all of the parameters, you need a baseline matter power spectrum that is accurate enough. And so what we are trying to do is to be able to have matter power spectrums at that redshift that go beyond second order perturbation theory, so that the rest of the parameters can be measured also in those ranges.
You're not necessarily including the measurement of the non-parameters, but you're trying to get the one you can have access to the ones.
Yeah, so I mean, the main constraints well, I guess we care about all of the constraints, so I don't want to say that we don't care about these constraints. But yeah, I mean, the important parameters are the DAO and RSC parameters for sure.
Omega n would be measured. One with a better precision than the one with
So I don't know the answer to that. My gut tells me no.
But then you can access all of the
Yes.
Can I ask a follow-up question to what you were saying?
Mhm.
So now you're exploring lambda CDM. Could you, so if you wanted to go to something beyond lambda CDM,
Mhm.
what would you do into, so now you're using Planck constraints, like would you do away with them, or like how would you go about doing it? Do you know that, or?
So that's probably an open discussion. I guess it depends on your model. But yeah, I guess the first thing that you will need is something like an embodied simulation on those spaces that you can then emulate here. And then you need to understand how the other physics that go beyond the matter power spectrum gets, which like what does galaxy bias means, or what does like any other parameters means in your new cosmology, and then yeah.
So your emulator and your embodied simulations, is that just like the simulations, or do you incorporate hydrodynamics?
No. These are gravity simulations. Yeah.
You're only looking at the scales behind.
Yeah, we care about big boxes at the moment, and
Is there anything else online? I don't think so. Oh, thank you very much then. Let's give me that.
thank you.